Yo, what's up, guys? Welcome back. I think we go to episode 120 today. Oh fuck. Sorry. Um, yeah, episode 120. Let's take a look at the Pokemon. We got a Staryu. Staryu. Let's take a look at the sound. So your Pokemon sound. Okay, I was not expecting that sound, but yeah. 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 Oh. Oh. Ah. Ah. There's that sound. Yeah. Let's go. Let's take a look at the problem of the day. Painting grid with 3 different colors. Let's take a look at this problem because that's a pretty high acceptance rate. I think we can do it. Painting a grid with 3 different colors. You're given 2 integers M and N. Consider an M times N grid where each cell is initially white. You can paint each cell red, green, or blue. All cells must be painted. Return the number of ways to color the grid with no 2 adjacent cells having the same color. Since the answer can be very large, return it in modulo 10 to the power 9 plus 7. I feel like my first intuition here is I feel like there's some sort of math formula for this. So I feel like this could be a math problem. It is a DP problem. Okay, I was wrong. Thought there'd be maybe some formula with this, maybe an easier way to solve it, but try to think here. Um, Take a look at the hints. Bitmars DP with state. Leetcode today Sri Lankan national flag algorithm. I'm not sure. I'm actually not sure where to start. I feel like I need to take a look at a video. Let's take a look at this one.
Hey everybody, this is Larry. This is day, okay, it's quick, but 18 of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. And today we have a hard. We have 1931 paint a grid with 3 different colors. Hit all the buttons. I just ran like 5-6 miles. I just came, or not just, but like it's been a week since I came back, and I'm trying to ramp up on the mileage. Man, I am not in shape. You lose it very fast, but you also regain it very fast once you very quickly if you have done it before once. So hopefully, this is the same with Leetcode, right? All right, let's take a look. First, I see a mod just peeking, so let's get the mod in there. All right. Okay, so what is it? So you have a grid. Consider all each cell is right. You painted red, green, and blue. All cells must be painted. Number of ways with 2 no adjacent cells. Okay. The key thing to note is that M is 5, so that's interesting. But yeah, I mean, I think this is one of those things where if you have enough practice, it does become a little bit straightforward. I don't mean to say this is easy, but they're really just, you look at the constraints and then you think, well, how to exploit the constraints, right? And for this, maybe I'll convert this to R and C, right? I always like R and C better because it just defines a little bit more. Also, I have crazy allergies because, I don't know, I was hanging out in Prospect Park here in New York City to watch other people do the Brooklyn half. But as a result, I think everything I own has pollen everywhere, and I'm just like, now I'm suffering. Because yesterday I was okay, but today I am suffering a lot. Allergies. Maybe I need to, okay, I'll do it afterwards. I was going to say, actually, I have quarantine here. But in any case, yeah. My apologies. But yeah, okay, so, well, so what does this mean, right? So I think it's just trying to figure out states, and states that are just fast enough. It doesn't have to be that fast overall. It doesn't have to grow fast or grow slow or whatever. It just has to be just fast enough for the constraints. And that is the basis for a lot of these dynamic programming things, right? And then here, well, I think the way that I would visualize this is that, actually, let me bring up the drawing thing. It's, instead of me trying to do more ASCII art. Right, for this one, I think one of the things that you may consider doing is just try to figure out, okay, if I'm trying to paint a cell, what do I need? Or what does it depend on, right? So here, let's say we have a grid, and of course, apparently R is much fewer than C, right? So you have a grid, and then now you're trying to look at this cell, for example, right? Then what does it need? Well, this cell, and let's just say for the purpose of loss of without loss of generality, we're going this way and this way, right? Doesn't, I mean, you could flip it if you like, if you prefer the other ways, right? So now we're going here. That means that all these are filled out, right? And then the others are remaining to be filled. And then now the thing is that, okay, well here, how do we choose a color that is valid, right? Well, we choose a color that's valid by not impeding on the previous one. So we need this. Obviously, we also need this because then we need these 2 things to not equal to this cell's color, right? And then, of course, if we're going to finish, then we go X and X. But the reason why we don't have to consider these is that, well, we will consider them in the future. Because when we fill out this, because one is they don't have color yet, but when they have color, then, there's a symmetry-ish thing of, for example, when we go here, then now we would consider it backwards that way, right? So we don't have to do it forward. And then also when we're here, we'll consider it backwards, right? So this is enough. And then now we consider, well, okay, that's fine, right? Then what do we need? Well, okay, so definitely we need the previous cells, previous columns item, and then also just the previous cell, right? And that's basically it. Because then now you think, okay, let's say we fill this color and then now we do another one, right? Let's say we now look at this one. Well, this one, we also need this one. So then now, that means that to fill out this row, or this column, for this column, we need all of each row, right? Each different thing of each row. And And yeah, right. Um, Maybe you could even say, I mean, there are different. No, I mean, and you also probably need the rest of this stuff too, right? And that's basically the idea.
I feel
But
like
then
this
the
explanation
question
isn't
is,
really the
well,
best, but
okay, you
it's
need
okay.
it, but is it fast enough? And that's where it comes in. Where okay, well, there's only 5 rows. That means that there's only at most 5 cells. Actually, this is 5 cells, right? That means that, and each of these has 3 colors, right? And that means that if we kind of look at it here, then the worst case maybe, use another color. Let's say this is the worst case because then now, actually maybe not. I mean, you can certainly require the last row, but actually you don't even need all of the last row because as soon as you move from this cell to this cell, then you don't even need this anymore. We don't even consider it anymore, right? So that means that you only need the last 5 things, right? So you need this, this. And each of these has 3 colors as we said. So that means that we need 3 to the 5th, right? So there's only 3 to the 5th number of previous state, right? 3 to the 5th times R times C for one for each cell. Each cell has 5 previous things, up to 5 previous things that we care. Up to 5 previous things that we care about, and that's it, right? And R times C is 5 times 1,000. Sorry, I'm just looking. Right, so that means that is 3 to the 5th times 5 times 1,000, which should be good enough, I think. Maybe, I don't know. Let's figure out the calculator real quick. What's 3 to the 5th? If I got done that, 243 times 5 is going to be a little bit more than 1,000 times 1,000 is 1,000,000, and we are good, right? And here, for each cell, we can just, in that case then, we can brute force all 3 colors. And that's it. And that, yeah. And so, yeah, that's pretty much it, really. And then now we just have to implement, right? Hopefully that was a good, like, visualization, right? So then now we have, I'm just calling them, let's just call them count, and then mask, and then XY, right? It's not a mask, sorry. It's not it is a mask, but it is, maybe it's not. Basically, you want a base 3 mask because the idea being a mask in this case, and actually maybe you don't even need to. Maybe I could actually do, okay, fine. No. Let's just convert this to an array, right? Let's just say we have an array. No, let's just do math. I mean, okay. I think I got this. Let's do it this way, and then we'll talk about it, right? And for for today, I know that sometimes for easier dynamic programming problems, I'll go over the dynamic programming mechanics. Today, just for this problem, we'll skip that part a little bit. I'll assume that you have the basic dynamic programming problem down. If not, then there are a lot of problems on Leetcode, and I have a lot of videos, so you probably could check some of those, and probably I will explain them because I did them more in the past, but today I can't keep my eyes open because of allergies. But yeah, okay, so then now if X is equal to R, then we're done, right? That means that we pass all the rows and then we're done, so then we return 1. I think that's good, right? And then we have total for the count, return total.
I don't like this guy's explanation, to be honest. Three colors. Yeah, we're gonna skip this today. I'm not sure. I'm not sure about the problem. I don't really know where to start, so maybe we should probably look at some other problems. Take the L on that one. Yeah, that was tough. That was tough. I wasn't just sure how to visualize it. I looked at some, put it into GPT just to see the kind of how it works, but build compatibility between rows, like compatible is equal to this, 4 row invalid rows. I need more of probably like an explanation to have a look at it, but it's alright. We did this one. Take a look at interleaving string. 42% acceptance rate. Strings S1, S2, S3 find where the S3 is formed by interleaving of S1 and S2. My calf, bro, jeez. Interleaving string. Trying to think if it's kind of similar to the problem we did the other day. Let's take a look at Nico's video, dude, because I'm not sure.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve interleaving string. So in this problem, we're given a list of 3 strings. Well, not really a list, but we're given 3 strings, S1, S2, and S3, and we just want to know a simple question. Can we form the string S3 by interleaving the strings S1 and S2? An interleaving string is basically when you take 2 strings and split them up into, substrings, and then you add them together. Now, they have a description over here, but I kind of feel like this description actually just made things more complicated for me, like with the absolute value difference being at most 1, taking these strings, forming them together. Basically, what we're saying is, can we take the string 1 and string 2, split them into substrings. Like you can see a string 1 is split into this one, and this one. And notice how the relative order of these 3 is maintained. That's very important. And this other string was also split into 2 portions, this one, and the relative order of the characters was maintained. You can see that this DB.
I'm kind of thinking. I feel like we need some DFS problem. Like we need some like 2-pointer solution that's pointing to these. If we can find them that are together,
ABC,
then we can move the pointer, you know? Okay, if we see B, we see B. You know, so we go AA, this is a group, then we see B, we see a B here, we can take it off. We see a C, we can take it off. And we see another C, we can take it off. But could there be multiple different ways? That's the thing, I'm not sure.
E goes in the front and the A goes at the end. So the relative order is important, but that's it. We can split the strings in any way that we want and then add them together. And we just want to know, doing that, can we form the third string? So the first thing you might notice is, well, if we're taking these strings, splitting them, of course, the total number of characters has to match the total number of characters in string 3. And yes, that's true. It will have to match, and in this case it does. We have 10 characters in the output, and each of these strings is 5. 5 plus 5 equals 10. So once you kind of understand what an interleaving string actually is, the logic of this problem isn't too complicated, right? For example, we see that the first character in string 3 is A, right? So for sure we need at least one of the characters from S1 or S2 to start with an A, right? Because we can't just take an A from the middle of one of these strings and then say, okay, we'll put that at the beginning, because remember, the relative order of each of these strings has to be maintained. So at least one of them has to start with an A, and we can see that the first string over here does start with an A. Right, so it's kind of brute force. We're just comparing the first positions of each of the input strings, right? So now we have a D, and we can choose between an A and a D in either of the strings, but we're looking for an A in the target string, so we're going to again pick from the first string, and we can cross that out. So now we have another sub problem. We have the remaining portion of this and the entire portion of this string, right? So, and we're kind of just brute forcing it. Obviously, if we got to a character such, let's say at this position we had a Z, but when you look at both of the strings that we have, neither of them have a Z. In that case, it would basically mean it's impossible for us to continue at this point. But what if we had the opposite? What if we had a B over here, and you can see that this position is also a B, right? And let's say we were looking for a B, right? So then which one of these are we going to take? Are we going to take the B from string 2 or the B from string 1? That's the backtracking or the brute force portion, right? We could take either of them. So we pretty much have to make a decision in our decision tree that we are going to choose both. We're going to see if we do it either of these ways, is it possible for us to take these two strings, interleave them together to build the output string, right? Because maybe one of the ways works, but the other way doesn't. We do have to try both of the ways, but it turns out we can use a dynamic programming technique called caching, where we can eliminate a bunch of repeated work. So therefore, the time complexity of the solution can actually be broken down to M times N, where M is the size of one string and N is the size of the other string. And you can actually, instead of doing caching, you can actually do a true dynamic programming solution that will also give you this time complexity. I'll explain a little bit about both of those. So let me just kind of show you what the decision tree for this problem would look like, and then how we're actually going to do the caching. So notice how we're going to start at the beginning of both of the strings, and we're also going to start at the beginning of the third string, right? We're looking for this character. Can we get it from either of string 1 or string 2, right? So that's kind of how our decision tree is going to work. We're going to have one pointer, let's call it I1, which is going to represent what position we're at in S1, and we're going to have another pointer, let's call it I2. 2, it's a little bit messy, but I2 is going to represent the position we're at in string 2. And we're going to have a third pointer over here. Let's call it I3, right? But do you notice that this pointer is always going to be the addition of I1 and I2? If we add these pointers together, we're always going to get this one, right? Because notice how, you know, they're both initially at 0, right? 0 plus 0 is going to equal 0, which is the first one here. If we increment one of them, right? If we take this pointer and shift it over here, this is going to be 1. So we're going to take 1 plus 0, add it together, and we're going to get at the position 1, which is going to be over here. And that makes sense because if we use a character from here, that's going to take up the character that's over here. So that's kind of how the math works out. So in reality, we just have to keep track of 2 pointers. The third pointer can be calculated for the position of this string. So we start at the position 0, 0. The first 0 indicates what position we're at over here. Second pointer indicates where we're at over here. And we're going to compare. So does this equal this character? Of course it does, right? D does not equal A, but A equals A. So we can shift our pointer over here and shift our pointer over here. So in this case, we didn't have to make 2 decisions. We just had an easy job. We just had to make 1 decision. So let's call that 1, 0, because we shifted our first pointer to the position 1. And now I'm going to go kind of fast because I think you probably get what we're going to do. So once again, this is the character that matches in string 3. So we can shift both of our pointers to the next position. And once again, we incremented the first pointer. So we're going to be at 2, 0. And in this case, B does not match D, but this character does. So once again, let's shift our pointers by 1. And in this case, we shifted the second pointer, so let's call that 2, 1. I don't really know why I'm drawing the decision tree like this, but let's continue. So in this case, you can see we're looking for a B, and we can get a B from this one or from this one, right? So that's going to be 2 different decisions. We finally have 2 different decisions. We can either do 3, 1, or we can do 2, 2, depending on how we do it. So this is kind of where the complexity is going to come, right? And the worst case would be that we could make 2 decisions every single time. So you can see that if we continue drawing this out, the worst case time complexity for a particular decision tree could be 2 to the power of n plus m, basically the total number of characters that we have. But you can see that we might be repeating the same subproblem multiple times. Right? How many different possible pairs of values could we even have like this? Well, we could only have n different values in the first position. We could have m different values in the second position. That's where the time complexity n by m comes from. So we can do this by caching. I'm going to show you how we can do that in the coding portion. So this will make sure that we have this many subproblems, and if we repeat the same subproblem, we can just do it in O of 1 time because we're going to be caching the result of that. Now, what exactly is the value that we're going to be caching? Well, for any particular subproblem, like for either of these branches, we want to know ultimately from here, are we actually able to form the remaining portion of the result string? So either it's going to be true or false, right? We're not storing a value like a number or anything. We're going to be storing true or false for any of these. And actually, if we find a single true, then we don't have to cache it, because if we find a single true, that means we are able to form the result string, and then we can immediately return true by going back up to the root that we called this recursive function from. So we discussed the memoization solution, but let's go over the true dynamic programming solution, which is going to be pretty similar to what we just talked about. So just to quickly go over, what was the base case in our recursive solution that we went over? Well, what would happen if, let's say, the last...
Okay, I think I understand. So what I'm going to do is I'm going to have this to the side. Okay, so obviously we're going to check, okay, well, if the length of S1 plus the length of S2 does not equal the length of S3, we're going to return false, right? This is our base case. We're going to have a backtracking function, right? We're going to have I1 and then I2. Right, and we're going to do, well, I guess if I1, I2 is greater than equal to the length of S3, we can probably just return, right? I don't know if this is the correct base case, but okay. Let's take a look now. So what do we need to do? We need to check, okay, well, let's check if I1, if S1, I1 is equal to S3, I1 plus I2. And let's do and S1, sorry, S2, I2 does not equal S3, I1 plus I2, then we can do something, right? Else if S1, I1 does not equal S3, I1 plus I2, and S2, I2 does not equal, sorry, is equal to S3, I1 plus I2, then we can do something. Otherwise, that's if they're both the same. I guess else if S1, I1 does not equal S3, I1 plus I2, and S2, I2 does not equal S3, I1 plus I2, then we can literally return false, right? Because you just return false, right? Else, this is where we have two decisions, right? So here what we're going to do is we're going to call, okay, backtrack I1 plus 1, I2. We're going to call backtrack I1, I2 plus 1. And here we have two decisions. We're either going to go okay, backtrack I1 plus 1, right? I2. Or we're going to go backtrack I1, I2 plus 1, because it could be either. I guess if we've gone through this, then I guess we can return true, right? Because if we've gone through this and we found out we backtrack here. Backtrack 0, 0. I guess we'd have to return this. Return backtrack 0, 0. String index is out of range. Why are we getting a string index out of range? I1 is less than the length of S1. I2 is less than the length. There's definitely a better way to do this than S2. I don't know why. Ah, shit. We forgot to return. I1 is less than the length of S1. And S1 I1 is equal to S3 I1 plus I2. backtrack I1 plus I1 I2, or I2 I1 plus 2. Okay, now this should give us a TLE. One-time error. String index is out of range. Now this should give us a TLE. Okay, now we need to add memoization. So okay, so we can do, well, x1 is equal to backtrack. So if I1, I2 in DP, we would return DP, I1, I2, right? Memo. And if we see X1, equal to X2. return dp ij. Okay. Just return false here. I think that can be fine. Add some caching. I don't know if this will submit. I think we need something over here too. Oh, no, it submitted. There we go. Option 1 is equal. Option 2 is equal to this. You can get rid of this or. Alright, then we can do, okay, well, dp I1 I2 is equal to option 2. Yeah, because at least one of them is going to be true, so makes it faster. Made it slower. Okay, right. Interesting. Full DP solution. Nice. 2DP, 2DP. Take a look at Alien Dictionary because I did want to take a look at it. Bro, it's locked, bro. How much is premium? 35 a month, dude. Bro. Why would you pay $40 a month when you can pay $13.25 a month? Like, bro. Jeez, man. Interesting. Okay. Well. I feel like we've gone through some of the most advanced algorithms. Yep. I think I've done insert interval. I remembered. Yeah. Oh, we can do that. Merge intervals. It's definitely not good with interval problems. A little tough. Oh. So we can see that one overlaps here, but these don't. Okay. We're gonna solve this problem. I'm just gonna go to the bathroom and then I'll be back. So we'll be back in a second. Okay, I'm back. Let's take a look here. Get an array of intervals, start and merge all overlapping intervals and return an array of the non-overlapping intervals that cover all the intervals in the input. Okay. Trying to think here. So if these two overlap, then we would need to combine these two, right? So we would combine the first one with the last one, right? Can we sort these based on .56 merge intervals? Okay, so who should we have to sort first? So we're gonna have to use probably a lambda function, right? So let's do intervals is equal to how to sort using lambda. So sorted intervals is equal to sorted. You want intervals. Key is equal to lambda x to the 0, I think. Print sorted 0 meaning the first number, right? Well, like the first number here. One, 3, 2, 6, 8, 10, 15, 18. Okay, I think that worked. Okay. So now we would need to try to think the best way to do this. Probably can we keep track of 2 pointers, right? Move 2 pointers like this. Let's do for cur in let's do the length of sorted intervals. Alright, we can compare. Okay, well, prev is equal to cur minus 1. Alright, so now we've got, okay, well, if prev really we're only comparing these 2 values, right? These 2 values. So if check, okay, if cur 1 sorry, if cur what's the logic here, man? If cur cur 0 is less than or equal to prev 1, then we know we need to compare, right? Sorted intervals prev is equal to cur minus 1. If cur 0 is less than or equal to prev 1, then how would we merge? Let's do some sort of like res array so we're not doing it in place, right? So we know this. If it's not, right, then we can simply just res.append. We can append our cur, I guess, right? What we do here, we do so then we do new is equal eval is equal to, it would be prev, right, 0. And then the max between prev 1, cur 1. Then we do res.append eval cur. We would return res. This is definitely going to be wrong, but at least I wrote something like invalid syntax. I think I'm missing a parenthesis here. Object is not subscriptable. Getting a type error. I don't know how I didn't realize that. Cur -1. Oh, I didn't think about that. That's how I would fix that. I would initialize it with the first in it. Cur is equal to sorted intervals I. If cur 0 is less than or equal to prev 1, then we merge. So we do So this is where I messed up here. They do... Well, because we know Prev 0 is always going to be the lowest one, right? So that's fine, right? So then we do max, that's guaranteed. Then we do Prev 1, Cur 1, right? But then this is never added. But where are we at? Oh, always comparing here. So getting the latest interval here, that's so smart. I didn't think about that. Then we compare Cur, sorted intervals I, right, which is where we're at in the array. So if there's an overlap, right? That's such a smart way to do it, bro. I didn't think about that. I was thinking about doing it like, you know, where you're actually manipulating the data, but here they're using this, right? So our previous value, when we start from here, our previous value is already in res. We get that last value, right? Then we compare these two values, right? So if Cur 0 is less than Prev 1, then really the only thing we need to change would be the last element in res, right? Which is exactly what we do, right? So we edit that, right? Our first value here is going to be 1.6, and then we just keep res.append, res.append. That is so smart. Wow. Non-overlapping intervals. Non-overlapping intervals. Given an array of intervals where intervals I is equal to start and return the minimum number of intervals you need to remove to make the rest of the intervals non-overlapping. Ow. and non-overlapping. Okay, so we're just like literally keeping track of intervals that overlap. So these intervals overlap. Oh wait, no, this one overlaps. So really, we're not doing anything now, we're just literally counting. Oh, dude. I need to stretch, bro. Oh, my back. Probably want to sort here again, so... Under function to sort Python. Let's do sorted vowels, right? It's equal to sorted intervals, key lambda. We want to do it off the first value, right? Let's print our sorted vowels. One, two, 1, 3, 2, 3, 3, 4. So this is where we see that it's overlapping, right? So really we can do the same thing, right? We can do, okay, so for I in range length, right? I guess we can do like a subprev is equal to 0. We start from 1 and go to the length of the intervals, right? So what we can do here is we can compare. So let's do, okay, so if sorted, this is kind of annoying me. I want to change this. Sorted vowels, right? Let's do sorted vowels is equal, oh sorry, current is equal to sorted vowels I, right? Then we have our previous, which is equal to sorted vowels. Let's make this J, right? Okay. So if cur 0 is less than prev 1, right? Then we would increment our count by 1, right? Otherwise, I guess we would just continue, right? There's no way that's it, right? Count is equal to 0. Don't count. There's no way that that's it. There's no way, bro. There's no way. Like, no. Okay, that's what I thought. There's no way it's that easy. Like, intervals 1. Mm, 2 to 12. Okay, so we're gone. We're like looking at these values, right? And then we're skipping, going here and here. And skipping, going here and here, right? So we need to like have some sort of while loop, I think. So I'm thinking but we're not comparing properly. We're not even incrementing J. What is going on here? Let's make this, let's turn this into a while. Make our I is equal to 1, and we'll go, okay, while I is less than the length of intervals. Okay. We can actually change this, probably. Okay. We loop through. Okay, we get our cur is equal to sort of vowels I. Prev is equal to sort of vowels J. If cur 0 is less than prev, right? So if it's in the loop, we want to increase I by 1 and increase and keep it the same, right? Is that what we want to do? If they don't overlap, right, then we would just increase I by 1. And increase J by 1. Guess we can get rid of this continue. I can see why it's a 40%, 55% acceptance rate. Okay. How many code went to? Problem with your code, when two intervals overlap, you're always moving I forward and keeping J fixed. Well, that assumes you're always removing cur, which might not be optimal. To minimize removals, you should keep the interval with the smallest end time, since this gives more room for future intervals and reduces weight overlaps. What did I sort it off? We sorted off the first value too here, right? Okay, we sort by 1. Okay. Sorted vowels 0, 1. Iron range 1 for length. Sorted vowels. Okay. We go cur star. We make our count, and then we need an end, which is sorted vowels 0, 1. pair. We go through this. We have a cur start, cur end. Cur end is equal to sorted vals I. Okay, so now we need to check. Okay, so let me visualize this really quick. Okay, so one, two, two, three. It's not overlap, but if 1 is less than 3, then we know it's an overlap. So if cur start is less than end. Cur start is less than end, then we want to increase the count by 1. Otherwise, we'd have to move our end, right? End is equal to cur end. Then we return our count. Nice. And we'd be approaching 400 problems soon, I think. Like, gotta be close. 389. What badges are there on Leetcode? I'm curious. So close. We're nearly done with the Leetcode 75. There's some good ones to redo though, like, for sure. Let's finish off with the leader node and a BST. I feel like it's been a while since we've done one of these, like March 11th, yeah. Given a root node reference of BST and a key, delete the node with the given key in the BST, return the root node reference possibly updated to the BST. So we search for a node to remove, we're given the key. The key, I believe, should be unique. Each node has a unique value, okay. Let's do like def recursion. We want to pass in our node, right? So let's pass in recursion. We give our root node, right? So base case would be, well, check, well, if code of val is equal to key, then I feel like we'd have to keep track of our previous a little bit, right? Because I don't think you can just delete from a BST like that. I feel like we'd have to somehow keep track of our previous. Because our 4 would move up there. What are we returning here? Tree node. I guess our base case should be this, no? Code of val is equal to key, right? We probably want to keep track of a previous, okay? I think. So we pass in our root, and we'd probably pass in none for now, right? The recursive case should be, okay, well, we would probably go, well, recursion, node, recursion, if node dot left, let's do recursion, node dot left, if node dot right, recursion, node dot right. Left and our previous would just be node, right? So we get to here. Code of val. Okay, if we get to this value, right? Okay, we'd have to return the right node, right? So the right node has to be moved to here. Man. I'm not sure. I want to make sure I'm doing the right thing. Ooh. Yeah, geez, it's been a while since I've done this one. Oh. Whoops. Okay, let's study this again. If not root, we return the root. Okay, we have to traverse based on the key. If not node, we return node, right? I believe this would go outside. If not, well, this needs to be root. We would return root, right? Otherwise, we would loop through. Okay. We check. Okay, so if key is less than no dot left, right? Then we'd have to obviously go no dot left, right? So we go recursion, no dot left, and our node here, right? Else if our key is greater than no dot right, then we would want to recurse the right subtree, right? Otherwise we'd have an else statement here. Okay. Inside of our else statement we have 3 cases, right? And they talked about this, so GPT said, right? We have case 1 where node is a leaf, okay? And we have case 2 where the node has 1 child. And then we have case 3 where the node has 2 childs. Okay. Okay, so if the node is a leaf, if not root dot left, not root dot right, and we would just return none. The node has 1 child, so if not root dot left, and okay, or not root dot right, we'd want to return root dot left if root dot left, else root dot right. Case 3 if it has 2 children. Temp is equal to root dot left while temp dot right. We have root dot val is equal to temp dot val dot left is equal to think I want to watch Neetcode's video again. Delete node.
What makes Augment different is its speed and deep context engine. It responds almost instantly, even on massive code bases, and can answer complex.
Hey everyone, welcome back, and let's write some more Neetcode today. So today let's solve the problem delete node in a binary search tree. We're given the root node of a binary search tree and a key value, and we want to delete the node with the key value, of course, and then we want to return the new root of the tree. Maybe the root changed, maybe it didn't. That's kind of what they tell you here. It's pretty rare for Leetcode to give you a hint like this, but you got to take what you can get. And they even give you how to break down this problem. You have to search for the node that you want to remove and then remove the node. If only it were that easy though. This problem can be surprisingly tricky the first time you solve it, especially if you don't have like a deep understanding of how binary search tree operations work. But we can use the properties of BSTs to our advantage. Let me show you how I'm going to do that. We're given the root of the tree. We're given a key 3 in this case. We want to find it. Now, finding it is not going to be too bad. We know we can do that in log n time. Well, that's assuming the tree is balanced. It might not be balanced. So actually a more correct way to say this, we can find this using the height of the tree. That's all we're going to have to traverse. But after we find it, we also have to delete it. Finding it is easy. We just take the root value 5. Is 3 greater than 5? Nope. Is it less than 5? Yes, it is less than 5, so we search to the left. And we would recursively just keep doing that until we find the value. Now, hypothetically, the key value might not even exist in the tree. In that case, we don't have to do anything, so that's pretty easy. But in this case, it does. So what do we do with the value once we have found it? Of course, we want to delete it. You might first think that, well, you got to get rid of this node, and you got this pointer over here, so instead of pointing it at 3, we should point it somewhere else, and we have to like move these nodes around. That is technically possible, but if you even try to code it up this way, you're going to quickly find out that it can get pretty complicated, because once you get to the 3, you're still going to need a reference to its parent. So that's going to be kind of complicated. There's actually an easier way to do this. It's a bit clever, and that is we can replace the value of 3 with a different valid value. We could pick any value in this tree. Why not pick the 7 over here? Let's get rid of this 7, maybe just delete this node and then put a 7 over here. Well, there's 2 problems here. One, when we put a 7 over here, does this still look like a binary search tree to you? Not to me, because every value over here should be less than 5, but that's not the case. 7 is greater than 5. So that's the problem. We have to preserve the properties of a binary search tree. And second, well, if we put the 7 over here, then we still have to delete a different node anyway. So how did that happen? How can we prevent that? Or maybe there's something clever that we can do. And yes, it turns out that there is something clever. First of all, what value should we replace 3 with? We should probably pick a value in this subtree if there's one available to us. The reason is because we know every value in this subtree is already less than 5, so we are allowed to replace this value with 2 or 4. But we really have to think through a bunch of edge cases for us to choose the most intelligent value. Let me tell you why. First of all, what would happen if this 3 over here actually did not have any children? Well, in that case, it would be pretty easy to delete this value, because what we're going to do recursively, I'm going to tell you that we're going to solve this problem recursively because it's a lot easier to do so. What we want to do is recursively delete from this tree, and then recursively delete from this tree. Once we delete from this tree, we want to return the new tree up to the parent, and then we want to return this tree just from our outermost function call. But what would we return from here once we delete 3? We would return null, of course, and this null value that we're returning is what this parent is going to assign to its left child. Whatever we return from here is what's going to be assigned to the left child of 5. So basically what I'm getting at here is if 3 has no children, we return null. What happens if it only has 1 child though? What if 3 only has a single child? 2. Now this child could have some children, or it might not have children. I'm arguing to you that whether it has children or not doesn't actually matter for us, because we know this itself is a binary search tree, and if we get rid of 3, all we have to do is say that 5's new child is 2, which is a binary search tree, and every value here is going to be less than 5. And of course, the exact same thing would be true if 3 did not have a left child, but instead had a right child only, and maybe it had some children, or maybe it didn't. It wouldn't matter. We would replace it with this new subtree regardless. So to summarize, a really elegant way to write this code would be, if 3 does not have a left child, return the right child. What if the right child doesn't exist? That's okay, because this is null, and that's exactly what we want to return to the parent anyway. And if 3 does not have a right child, we return the left child, because if it exists, we return it great. If it doesn't exist, we return null, which is what we would want to return anyway. So that was the first step. Now let's go on to the second step, which is a bit more tricky, I think. Now, of course, in this example, we actually do have 2 children for 3. So what we actually have to do is replace the value we have here. We can pick a value from the left subtree or the right subtree. This is a pretty simple tree, and I can't really add additional values to 4 because I can't really add a 1. That would not make this a binary search tree, but just pretend like we have some dummy value here that is valid and some dummy value here that is valid as well. What we would want to do logically is pick an intelligent value from the right subtree. What value could we put here such that it would satisfy this being a binary search tree? If we pick 4 and put 4 over here, it's actually not going to be a binary search tree because this value is supposed to be less than 4. That's why it's the left child. But if we put 4 here, then X is over here. X is actually less than 4, but it's on the right subtree. That's not what's supposed to happen. So when we pick a value from this right subtree, which is what I'm going to do, you could pick one from the left subtree, but I'm going to pick one from the right subtree. I'm going to pick the smallest value, aka the minimum value from the right subtree. Every value in the right subtree is greater than 3, but we want to pick the smallest value because if we pick the smallest value, then we know that every value here is still going to be greater than the value here. Now, how do we find the smallest value from the right subtree? That's the easy part about a binary search tree. You just basically go as left as you can. You just keep going in the left direction. You keep going left until you can't go left anymore. That's the minimum value. And then you put that minimum value over here. In this case, it's going to be 4. And then what you do is recursively, and this is kind of the hard part, you probably wouldn't think of by yourself, you recursively call delete node on the right subtree over here. Because remember, if we put 4 over here, now we have 2 4 values. That's not what we wanted. So we have to recursively call delete node on the right subtree, passing in not 3 anymore. We're not trying to delete 3. Now we're trying to delete 4. So in that case, we will actually end up with a chain of recursive delete node calls. First, we delete the value 3, and then we want to delete the value that we replaced 3 with. So then we want to delete 4. And it's actually possible that 4 had a right child. Let's say it had a right child of 5, even though 5 is already here. Let's just ignore that. But if it had a right child of 5, we'd put the 4 over here because 4 is the minimum. We can't go any further to the left, but now we want to call delete node on this tree, passing in 4. So then we get to the 4. Now we want to delete this 4. So we again pick the minimum value from the right subtree, which in this case is 5. We would delete this node, and then we would put the 5 over here, and then we would call delete node on this subtree, deleting the 5, and then possibly we would just keep calling that recursively. But the smart thing here is that we are pretty much iterating through the height of the tree as best as we can. There are portions that we are going to have to visit twice, but if we have to visit a portion of it twice, the worst case, this would be 2 times h. So still the time complexity is the height of the tree. Now let's code it up. That was a long-winded explanation, but the code is actually not too bad. So generally with recursive problems, we want to start with the base case. So if the root is null, then we just want to return the root. There's nothing for us to delete anyway. Otherwise, we want to find the node that we want to delete. So if the key value is greater than root.val, then we want to go to the right, which we can do like this. So self.delete node, passing in root.right, passing in the exact same key value. Else, if the key value is less than root.val, then we want to call delete node on the left side of the tree. So on the left subtree, passing in the exact same key value. Now the last case is that we actually found the node that we want to delete. So this is where we actually do the deletion. Now you might have forgotten, but remember there's actually some simple cases. Root is the node that we want to delete, but what if the left child of root is null? Then in that case, we know the new subtree that we want to return to the parent is going to be root.right. We don't have to do anything super fancy. And otherwise, if the right subtree is null, then we return root.left, which actually reminds me, when we call delete, well, first of all, over here, we should call this delete node. And when we actually call these deletions, we might be deleting the left child itself. So we probably want to take this updated binary tree and assign it to root.left. Imagine if this was the base case that executed. Instead of returning the root that was actually passed into this function, now we want to return root.right. So in that case, we would want to take the return value of this call and assign it to however it was called, whether it was the left child or the right child. So let's do that up above as well. Now for the slightly more complicated part. So now we want to find the minimum from the right.
Your father knows about saving money. Everything I'm wearing, I've had since boot camp.
Subtree, just like I showed earlier. The easiest way I think to do that is just to take the current pointer and assign it to root, because we are going to still need the root. And then while cur.left, we're going to keep going down the left child. The reason I'm doing this is because we want to make sure we stop at a valid node. We don't want cur to stop at null. So by the time this is done, cur should be pointing at the minimum node in the right subtree. And remember, what we want to do with that minimum value is replace the current root value with it. So we say root.val is equal to cur.val, and then
root dot left, we return none. If node has one child, return root node dot left. If node dot left, else node dot right. Suture order make the temp while temp dot right. Node dot val is equal to temp dot val. Node dot left is equal to recursive node dot left temp dot val recursion root. There's no tribute val. Temp is equal to node dot left while temp dot right. This shit's pissing me off, dude. need to get through this code a little bit more. I don't remember doing this last time. I don't know if I got it or how I felt after it, but I definitely don't. I feel tired too, bro. Like. Hmm. is equal to temp.val, no dot layer. Okay, I think I understand. Okay, I'm gonna leave it at that. So, it was a little confusing. I appreciate you guys watching, and I will see you guys tomorrow.